Welcome back, everyone. I am very excited to introduce our second keynote speaker, Professor Noah Snavely. Noah is a professor in the computer science department at Cornell Tech. He's also running a research group at Google Research in New York City. Noah's groundbreaking and inspirational work in computer graphics and computer vision generally aims at reconstructing, synthesizing, and understanding our world through massive unstructured photo collections. You recently received the Helmholtz Prize for building Rome in a day, which we are all familiar with, and many other awards such as SIGGRAPH's Significant Research Award and the NSF Career Award. Today is going to talk about reflections. Please, Noah, take it off.
Okay, everybody, this is so cool. So because my talk live had some technical difficulties, I'm re-recording it canned, so this can live on and for posterity. So I'm just going to get started and include all of the fun interactive parts for those who want to play along at home. So the warm-up activity is to please get a piece of paper or anything to draw on. Imagine a clothes hanger in your mind's eye, and then draw what you see on a piece of paper. Draw a clothes hanger, please. Okay, so with that, I'm going to give a talk called On Reflection, and it'll be clear why in a moment. And this talk is somewhat philosophical, but I promise that it will relate back to computational cameras by the end. So please bear with me and we'll have some fun along the way. And although this may not work well if you're viewing this on the recording, you can still go to slido.com for the interactive part. So we're using Slido, which is interactive slide software. Go to slido.com and enter code NOAH. As long as you do that in the next few days after this is recorded, it will still work somewhat. At least you'll be able to see the results. Okay, so imagine you're Alice from Alice in Wonderland, and you come across a mirror that you can pass through to take you into the mirror realm. Okay, that's the basis of, that's part of the events of Through the Looking Glass by Lewis Carroll. So what would you see? So, well, there's a room that you can see through the glass that's just the same as our drawing room, only things go the other way around, right? Okay, so everything is reversed. And so there's some subtle things that happen if everything is reversed. And this, imagine further that you're Alice and you wake up one day and you can't tell if you're in the real world. You can't remember if you're in the real world or the mirror world. How would you be able to tell? What would clue you in? And this kind of fascination with mirrors and reflections and mirror universes has been the basis of a lot of literature, especially science fiction. And one of my favorite examples is a story from Arthur C. Clarke called Technical Error from 1950. And the synopsis is as follows. The first power plant to exploit superconductivity has been built, and worker Richard Nelson is laterally inverted, so mirror flipped, his body is mirror flipped, following an accidental short circuit in the facility. Nelson finds himself wearing his wedding ring on the wrong hand. Written texts appear mirror inverted, and coins in his technical diary have been affected. Nelson begins to starve. Normal food does not nourish him because most biological molecules are chiral, meaning they have a handedness. And if they're the wrong handedness, they won't work the way they're supposed to. So I love stories like these. I'm also very fascinated with this idea of reflection and how reflection changes the world. And so, okay, so here's the first quiz. Can you tell if this image has been flipped? So this is an image that is either a normal natural image or an image I've reflected. And you have to try and figure out whether it's real or reflected. Okay, that is left, right, reflected. So I'm gonna open up Slido. I'll give you, as if you can still play along at home. I'll give you 20 seconds to try and figure out if this image has been flipped or not. Okay, so this is the baked Slido poll results. The majority of people thought this was flipped. Indeed, it's not flipped. I didn't try and fool you. And how can you tell? Well, I cheated and I obscured some obvious cues that, well, if you happen to notice there's text in the background, I blocked it out in the version I showed a moment ago because text is too easy. But there's some subtle cues as well. It turns out the buttons on the shirt are a subtle cue. The pocket being on this particular side is a cue because, well, pockets are preferentially on one side of a jacket. And for men, the buttons go a specific way for, at least for jackets in Europe and the US. Maybe the way he's holding the newspaper is a cue and the bag. There's other possible cues as well. But this is not an easy task. The cues are fairly subtle. And that's true of the mirror universe. It differs from the real one in ways that are both obvious and subtle. The mirror universe, meaning the universe of images that have been left, right, flipped. And this is an interesting property of mirror flipping that's not true of other kinds of image transformation. So if you vertically flip an image, it's very obvious that the image is wrong because gravity is going the wrong direction. But if you horizontally flip an image, the cues that reveal that tend to be more subtle and more interesting and rich. So I'm very fascinated with this kind of idea of reflection from, I guess, an aesthetic point of view, but there are reasons why we should care in computer vision. So symmetry assumptions are actually pervasive in computer vision, and I'll show some examples in a moment. But actually the world is fundamentally asymmetric, even down to, as I'll show at the end of the talk, the camera hardware. The cameras we use to take pictures have very subtle and fundamental asymmetries to them. But we can also use symmetry assumptions in beautiful ways. So one of my favorite examples, I saw this when I was a prospective PhD student visiting UW, is this view morphing work from Seitz and Dyer from SIGGRAPH 96. And so, okay, think of the Mona Lisa, famous painting. It's a single painting, but if you flip it, because the Mona Lisa herself is largely symmetric, you get essentially a second view of the same person, okay? That's kind of magical. You get another image for free, and you can use that to do things like view synthesis. So you can animate all the images in between. You can generate a view of looking at the Mona Lisa from the front because you have a stereo pair, right? So if you have an image of a symmetric object, the insight is you really have two images. And you can carry that further and say, okay, well, I can use those two images to train. So from images of faces, you can, in a self-supervised way, learn to predict 3D shape, lighting, from this fact that you have an image for free. And that's exactly what this beautiful work from last year's CVPR, the Best Paper Award winner from Shang-Zhe Wu et al., supervised learning of probably symmetric deformable 3D objects, uses this insight to learn 3D shape and lighting from single images. It's just, I love it. Okay, so symmetry is magical in some ways. Here's just an animation of that. And we took that a step further in a paper we have at CVPR this year, where we exploit an even stronger form of symmetry, radial symmetry, or objects that are surfaces of revolution, like vases in museum collections. So essentially, we take all of the vases in the Metropolitan Museum's collection and learn to predict from single images full 3D shape. Again, it's simplified because of the radial symmetry, and material properties and illumination by using symmetry essentially as a form of supervision. Okay, so we can relight these vases too. We get these rich reconstructions by relying on symmetry. So symmetry is very powerful. And maybe the most powerful way it's been used in computer vision is as a form of data augmentation. Okay, so left-right flipping is a very common data augmentation operation used in recognition problems, all the way back to the pre-deep learning DPM, deformable parts models work of Gershik et al., where if you go back to Ross Gershik's old code from 10 years ago, you find that even then they were doing left-right flipping, I think in Pascal dataset back then, to generate more data. And the insight is that, okay, deep learning models require lots of data. We can instantly double our data by left-right flipping our data set. And that's great. That's a beautiful way to generate data. But it relies on the assumption that flipping an image somehow keeps you in the same visual universe, right? That flipping really gives you for free an image that's also a natural image. So is that really true? Well, is the visual universe flip invariant in some fundamental way? And of course, it's not. Here's an image, here's a flipped image. You can tell it's backwards. This is not what you might think of as a natural image because the text is going the wrong way, except in this case, I was tricking you. This is actually a natural image because it's a picture taken in a mirror. Mirrors exist, so you can get images of reflected things, but in some sense, this is an even more, makes the problem of understanding the asymmetry in the world even more beautiful and rich and intriguing. Okay, but there's lots of other examples of ways in which the visual world is asymmetric, and I've been collecting these over time, and I'll just show you some of my favorites. So the first one comes from old Radiolab episode. So Radiolab's a science podcast. There's an episode called Mirror Mirror where they use this example as an illustration of some kind of, I guess, psychological idea. So, but first, here's a quiz for you. One of these is, okay, these are both pictures of Abe Lincoln. One is the real Lincoln, and one is mirror flipped Lincoln. Okay, so your test is, which of these is the real Lincoln, A or B? Okay, so again, you can play along at home by going to Slido. I'll give you 20 seconds to look at these images and try and figure out which is the real Lincoln. This is so cool. Okay, so the answer is B. The Slido participants during the live talk figured, the majority got it right. And I find this example very intriguing because when I look at B, the correct Lincoln, I see how I think of Lincoln in my head, a dignified, leader. But when I look at A, I don't get that sense at all. It looks almost uncanny or somehow sinister. So why is that? Is there something fundamental about B that just looks more natural? I actually don't think so. In this Radiolab episode, they talked about things like, okay, maybe parting your hair one way makes you look more natural or somehow conveys something different than parting your hair the other way. I don't really buy that. I think what's happening is that I'm just very familiar with this portrait of Lincoln. So I know the real version of it, even though in some sense, these images are equivalent, right? They're just, they're the same up to a reflection. So for instance, one idea might be, okay, Lincoln's face is actually fairly asymmetric. He's suffered from what's called strabismus. One of his eyes was, the muscles kind of worked independently of the other one. So he's kind of staring off in a different direction with this eye. His nose is a little crooked. His lips are asymmetric. He has this bump on his face. Maybe I'm so familiar with this portrait that I'm mentally correct for those asymmetries to where it looks more symmetric. If I look at the flip version, I kind of correct them the opposite way and it looks uncanny. Perhaps, I don't know, just a guess. But I've definitely had the same experience looking at my own face. When I grew up, cell phones were not pervasive. I was used to seeing my own face in a mirror, which is flipped to how other people see it. So when I saw my own face in photographs, somehow it seemed off to me. I didn't like it. Similar to if you've had the experience of viewing your unflipped Zoom feed. But of course, maybe other people, who are used to seeing me as the regular me thought the exact opposite, right? Okay, so I noticed a qualitative difference between these two images. When I ran this poll on Slido, other people did too. The majority of people also noticed a qualitative difference between these two images. Again, probably because they're very familiar with this portrait. Interestingly, here's a beautiful recent computational camera work called Time Travel Photography from UW. First author is Xuan Luo, where they designed a method that would turn a historical photo into a photo, into the same photo as if it was taken by a modern camera. Okay, so this is Lincoln, as if you were captured by a camera of today. And somehow this doesn't look quite as asymmetric as, somehow this doesn't look quite, I don't get the same distinctive feeling of differences between these two images as with the black and white original photos. Maybe because this process of turning into a modern photo removed a little bit of the asymmetry. Anyway, this is great work and beautiful result from their work. Okay, this is so cool. So just one more example. So it's maybe cheating to use that Lincoln portrait because a lot of people are familiar with it. So here's a portrait of a person you may not be familiar with. And same question, which one of these people is real and one has been flipped? So which one do you think is real? And again, if you are so inclined, please, you can think about this for 20 seconds. If Slido still lets you weigh in, please go ahead. Yeah, which one is real person? Which one is flip person? Okay, so of the people who took this, actually everyone got it right. I'm not sure how they did that. I think it's very difficult to answer this question, but it is possible there are some subtle cues. And in fact, there are some that I'll talk about later, but none that I knew about that I could use to answer this question. Okay, and depending on how I ask this question, sometimes a lot of people get it right and sometimes almost everyone gets it wrong. Okay, so yes, so B is the right answer. Now, here's another example of an asymmetry in the world that might not be obvious until someone points it out to you. So in this case, this was highlighted by Antonio Torralba and Alyosha Efros in their work on dataset bias, where they pointed out that if you do a Google image search for mug, almost always the handle is on the right side, okay? And indeed, if you ask people to draw mugs, like has been done work in the psychological, has been done in the psychological literature on canonical views, people tend to draw the handle on the right side. And from a point of view of most people in the world, majority of people in the world are right-handed, that makes sense because that's how you would see a mug if we're sitting on the table in front of you. And probably they also put the graphic, that guides how they put graphics on mugs. And so at the beginning of this, I asked folks to draw a clothes hanger. And my guess was most people would draw it like A with a left-facing hook and not like B. Because, and indeed, if you look at the results of the poll, everyone said left-facing hook. And Google image search agrees with that. If you look for at least product photos of clothes hangers, almost all of them have a left-facing hook. And again, I think that makes sense from a majority right-handed world where, if you're hanging up a shirt hanging on a clothes hanger, you would naturally see the clothes hanger with a held in your right hand with a left-facing hook. Okay, like very not obvious until you think about it kind of thing. One more example of a subtle asymmetry. So it's well known that if you're interpreting an ambiguous image where the light source direction is ambiguous, people have a preference to interpret the light source as coming from above. So here's an example image where there's either bumps, some of these bumps are coming out at you and some are indented inwards, and the light's coming from the top, or the opposite. You switch which bumps are facing which way, and the light's coming from the bottom. And I interpret this when I look at this as light coming from the top. Most people do, because that's a ecologically sensible thing to do. But not only that, this work found that the preference is not for directly overhead, but shifted to the left, okay? And this preference is reflected in art spanning 2 millennia in that the light source in paintings more often comes to the left than from the right. And you can think about why that might be. But again, a very intriguing finding. And if you look at this portrait of Abe Lincoln photograph, the light's coming from the left. That might just be a coincidence, or this might be a bias that's baked into how people take photos. Actually, I don't know the answer to that, but that's an intriguing question to explore. So given all of this evidence for asymmetry, at Cornell, we worked on exploring this computationally. And we published this as a paper called Visual Chirality at ECCV last year. And this was work with Jicho Lin, who's now a PhD student at CMU, Jin Sun, Abe Davis, who's a new faculty member at Cornell, and myself. And so we wanted to explore this problem of, can we discover asymmetries in the world? We started with the concept of geometric chirality, which is chirality describes objects that, when flipped, become a different object. Okay, so a right hand, if you flip it, is no longer a right hand, it's a left hand. And this word phrase chirality, this coining goes back to Lord Kelvin in the 19th century, who called any geometrical figure or group of points chiral and say that it has chirality if its image in a plane mirror, ideally realized, cannot be brought to coincide with itself. That is, if you mirror flip a right hand, there's no rigid transformation that will transform it back into itself. You can't rigidly transform a left hand to coincide with the right hand. Okay, so it's chiral. And some other examples of chiral objects are corkscrews, golf clubs, and if it's complicated enough, molecules. So molecules, as I noted at the beginning, can have chirality. So for instance, a famous example of this is that the molecule that makes spearmint smell like spearmint, when mirror reversed, is the molecule that makes caraway smell like caraway. Okay, different smell. But your nose, despite the similarity of these molecules, your nose is smart enough to tell the difference between a right-handed and left-handed version of this otherwise identical molecule. Okay, and this is just a geometric property of these molecules. Okay, now let's think about the visual world. And let's think about the occurrence of right hands and left hands in the world. So one way to think about that is, imagine a distribution, a probability distribution that maps any image to a probability, how likely it is to observe that image in the world. And here I've drawn this cartoon here, where the images are just arranged on an x-axis, and probability d of x is arranged on the y-axis. Okay, so since right hands and left hands are, for all intents and purposes, equally likely in the world, you can imagine the probability of observing right hands and left hands is equal. But let's imagine a right hand positioned into a thumbs up and a left hand positioned in a thumbs up. Perhaps if you look at the distributions of these two symmetric, two images that are mirror copies of each other, maybe the probability distribution is not the same, because maybe it's more like you're more likely to observe a right-handed thumbs up than a left-handed thumbs up, because more people are right-handed than left-handed. Okay, so if I plot the probability of 2 points that are mirror images of each other as images, perhaps those probabilities are not equal. So we can define this concept, we call this visual chirality. Suppose you can assign a probability P of X to any image X. This probability distribution P is visually chiral if P of X is not equal to P of T of X, where T is the horizontal flipping operation. Okay, so if flipping an image turns it into an image with lower probability or a different probability than the original image, we say that the distribution of images is visually chiral. And this image is visually chiral, okay? So this is a property of distributions of images and talks about whether or not the probability of an image is the same as the probability of its mirror flip. Another way to put this is to go back to Abe Lincoln's face. So as I noted before, Abe Lincoln's face is asymmetric. But maybe you're as likely to meet mirror Lincoln in the world as you are to meet real Lincoln. Maybe there's nothing, maybe the way in which he's asymmetric is common across a lot of people. Okay, or maybe, maybe the flipped Lincoln and the real Lincoln are equally likely. Or maybe asymmetry is shared across different kinds of people. So, maybe the nose is preferentially bent in one direction. Okay, so we designed some experiments to tease out chirality in the world. So there's a very easy experiment you can do. In fact, you can take a bunch of images, try and flip half of them, and train a neural network classifier to tell whether an image has been flipped or not, okay? If the world is visually achiral, meaning it's perfectly symmetric, the distributions of images are perfectly symmetric with respect to horizontal flipping, networks should not be able to do better than chance on this task. If the world is asymmetric, it should be able to do better than chance, okay? So we took a data set of people because people, we figured, exhibit interesting achiralities. And indeed, in our first experiment, the network was able to achieve a very high accuracy on this task, which seems surprising. I think people would have much more trouble with this task. So we used some techniques, including GradCam, to visualize what the network was doing. And it seemed like the salient regions for chirality tended to be boundaries or low-level features that we couldn't quite interpret. So we tried to stop the network from doing what it was doing, and by data augmentation, like in particular random cropping. And then we got much more natural looking saliency maps and maybe more believable test set performance of 80%. But that's still very high. And it turns out that a lot of images have text, which is too easy. So we got rid of images with text, and then we got about 3/4 accuracy, which is still surprisingly high. So we wanted to see what was going on. Again, we ran GradCam on each test image to reveal the salient regions. So GradCam, you can think of it as making a heat map, computing a heat map where salient regions are highlighted. And then we took the feature, in the feature map at the most salient spatial location, took these across all test images, and just ran k-means clusters on these features. And if you look at these clusters, they tend to often be regions that are not surprising. Okay, so what the network learns, it seems, are things like shirt collars are chiral, visually chiral, because the buttons, again, tend to go a certain order. One side is on top of the other. That's different for men's and women's shirts, but it seems to be learning this correlation. Shirt pockets, which are preferentially on one side. Watches, which most people wear on the left hand. Guitars are somewhat symmetric as objects, but are held in a chiral way because they tend to be held for right-handed performers in a certain way. Camera phones, this is interesting because these tend to be photos taken in mirrors, but still reveal chirality in the placement of the camera lens and the logos, et cetera, that which hand is being used to hold the phone. So it's learning some very interesting things. And it's also learning about, surprisingly, a lot of these clusters seem to be about faces. So maybe there is something asymmetric about how faces appear in photos. And so we tested this by doing the same experiment, but on a data set of faces, f of HQ, and seeing if it could first do this task of learning flipped versus not flipped images, and trying to tease out what it learns. So again, it achieves surprisingly high accuracy on this task, 81% on the test set, which suggests that there is chirality in these images. And moreover, if you, without fine-tuning, apply the trained model to another data set labeled face in the wild, you still get better than chance accuracy. Okay, so if you look at the clusters that we are derived from these models, you see a few things. So it seems like hair part is a chiral feature. Perhaps it does seem like people tend to part their hair more often in one way than the other. Surprisingly, beards. So I don't quite understand this, but maybe if you're combing your beard with one hand preferentially, it leaves a chiral trace in your beard, or it could be that there's a concept of hair whirl, like which way your hair is spinning, clockwise or counterclockwise. This is a photo of my son, Charlie, when you could see a very prominent hair whirl when he was younger. And most people indeed have a clockwise hair whirl. Maybe that's reflected in the beard too. Eye gaze seems to be somehow reveal some chirality. So, there's a few different ways you could imagine this could come about. Like maybe people who have strabismus, like Lincoln, tend to have it in the same eye. I actually don't believe that, but there's a few other factors that could be, explain this. So like asymmetric placement of lens with respect to the camera body. If people are looking at the center of the camera, but the lens is off center, maybe that would explain this. Maybe people tend to pose their head preferentially in one versus the other direction. Or maybe ocular dominance plays a role. In addition to handedness, people have I suppose, an eyedness. The majority of people are right eye dominant. You think of this, it's like the eye you would keep open when you're shooting a bow and arrow. Okay, so we can learn a bunch of interesting chiral cues from images automatically. General images of people, faces. I want to return to those low-level cues that I mentioned earlier that we found when we first were attacking this problem. As I mentioned, without any kind of processing, the network tends to fire on boundaries or sometimes random areas without much logic to them. And these go away when you train with random cropping and other kinds of augmentations. So what's going on here? Well, we thought about this and we thought about the question, is there something inherently chiral about cameras that would reveal traces of that chirality in the image pixels themselves? And you can think about this problem like, okay, what about a camera could be chiral? And actually it was Bill Freeman who gave me the answer when I talked to him about this, or clued me into this, which is, I think, okay, so definitely one thing that's chiral is the camera sensor, or the Bayer filter that sits atop the camera sensor on most color digital cameras, where the Bayer filter masks out light according to frequency in such a way that you can reconstruct color images. And it has this characteristic, usually green, red, blue, green pattern in 2x2 blocks. And so here's a picture of the Bayer filter. This is chiral. So if you have an even-sized Bayer filter pattern, it's going to be chiral because if I flip it, at the top left corner is a red pixel instead of a green pixel. So that might be a subtle thing. And it is a subtle thing. Actually, if you flip it and translate it, it does match itself. But first of all, this is a instance of chirality, no matter how low level it is. And this has it turns out there's two things that happen here. One is that you get boundary effects. So you can tell whether you're on the left or right boundary because, by interpolating these colors like demosaicing algorithms do, what happens on the left edge of a even-sized Bayer filter is different from what happens on the right edge because you have a different pattern of pixels on those two edges. Okay, so that would explain why you might find chiral traces on boundaries. But even internal to a Bayer filter, what actually happens in a camera is more complicated than demosaicing. It also interacts with JPEG compression, and JPEG happens in 8x8 blocks. And there's a lot of details on what exactly happens here, but I think the crux of it is a JPEG block, even-sized JPEG block, involves a chiral, a region of a Bayer filter pattern. Okay, and you can also imagine, okay, what happens on the left side of a JPEG block might differ subtly from what happens on the right side of a Bayer filter block. The pattern of colors, the exact distribution of color patterns you get might be slightly different. And indeed, that seems to be what's going on. And the upshot is that we believe that every JPEG image in the universe captured with a Bayer filter mosaic has very subtle chiral traces embedded in it in a very low level pixel pattern. And so therefore, you can tell whether an image is flipped or not by looking for such patterns. Okay, so even if the distribution of natural images were perfectly symmetric, right hands and left hands and right thumbs up and left thumbs up were equally likely, you could still tell if an image has been flipped by looking at such chiral traces baked in by the camera itself. Okay, so we've learned a bunch of cool things, I think, about the world. So what are the applications of the work? Well, first of all, informing better data augmentation. So I think it's not true that you can just flip images and treat them as normal images, but maybe by thinking about this chirality, visual chirality, you can come up with better data augmentation schemes. Self-supervision of visual representations. Well, we're learning automatically things like watches and so on. So maybe this is another kind of task you could use to learn self-supervised representations. Maybe you can come up with camera hardware that's adapted to unbalanced distributions, this visual chirality. Image forensics. Well, now we have another tool in our tool belt to see if an image has been flipped or not. That might be useful for determining fake images. Visual discovery in general. I'll return to this, but finding out subtle and not obvious information about the visual world. And one fun one is just mirror detection. So there has been work in 3D reconstruction on detecting mirrors in scenes. And I think chirality is another tool for potentially detecting when something is a reflection of something. And it's just fun to think about. I really am intrigued by these kinds of, well, in a sense, visual discovery. So using image collections and learning to discover subtle visual correlations. I'd like to see a lot more of this in the vision community. The kind of work like what makes Paris look like Paris from Dorsch et al. Shir Guinnessar's work on understanding changes in portraits over time by looking at yearbook photos. Timnit Gebru's work on using Street View to understand demographics. We've done some work on understanding fashion trends from large-scale imagery, like do people really wear white after Labor Day, kind of thing. Or I forget if it's wear like white before or after Labor Day. But you have to be careful not to discover spurious correlations. But I really feel like computer vision, now that we have deep learning, is a great tool for discovering subtle visual correlations in our world. Okay, so with that, I'd like to thank my co-authors on this work and thank you for all of your attention. Thank you so much and hope you all have a great day. Bye-bye.